Yeah, welcome to the presentation about CausalSpartan, which is a protocol that ensures causal consistency for distributed data stores. It uses the principle of hybrid logical clocks, which we already covered in the class, but no worries, I'm going to recap quickly anyway. So let's start. Yeah, let's first come to the contributions of this paper, but maybe before that, if you haven't watched the Gentle Rain video, which is another video of the video series here in the class, you should probably do that beforehand because CausalSpartan is an improvement of Gentle Rain, and to follow this presentation it might be very useful to have seen the Gentle Rain video beforehand. Again, CausalSpartan is a causally consistent data store which is resistant to a clock skew among servers. A clock skew means that the physical time between servers is different, and basically this idea introduces the hybrid logical clock instead of using directly the physical clock as it's done in the Gentle Rain paper. In general, two issues are addressed. First, the latency of put iteration is reduced when we do have clock anomalies, and second, the data visibility latency is reduced. Also, there is an experiment to demonstrate efficiency, and finally they also present an impossibility result. So we do have the assumption for this study that one client speaks only to one server. However, if one client speaks only to one data cluster, but if one client would be able to speak to several data clusters, then we would have issues regarding the causal consistency and also the availability. But this is going to be the final proof in my presentation. Now let's quickly recap the happen before relation, or in general the causal consistency. So first let's come to happen before. We have the same three cases as we've had with the events. The first case, if two events happen at the same client and one event happens before the other, we do have the happen before relation. The second is a bit different. So if the first event is a put event on key k, and the second is a get event also on key k, then we can say, and the get event returns the value which was actually written by this put statement. Then we can say that this put statement here happened before this get statement here. And the third one is the transitivity we've had before. Now the causal consistency is defined if via the dependencies. So let's say we're having a version v1 depends on version v2, and this is only true if the put statement of k1 v2 happened before the put statement of k1 v1. Why is this the case? So if the put statement here happened before this put statement, then obviously the v1, which is the second put statement, depends on the first put statement. So basically we can then say just the version of v1 depends on the version of v2. And finally, the causal consistency. So let's say we're having two keys and two values as we have seen before, and v1 depends on v2. Then we have to make sure if a client has read v1, then v2 must be visible. This is the important word here, because we know that v2 depends on v1. So if we have read v1, v2 must be visible. In case v2 wouldn't be visible, this would violate the dependency relation, and therefore the causal consistency. Now let me make those definitions a bit more concrete because it's necessary to understand the final proof. So let's assume we do have a replica or data cluster ds, and we do have a key, key1 and key2, and let's say we do have here the initial version, which is v1 init, and here we're going to have v2 init. So then we execute the following statement. So first, client A executes the put statement for key 2. So then we append for this key the version v2, and then client B executes the statements and gets the value of key 2, which is v2. So we basically know here we do have now a happened before relation because we have a put statement on key 2 and later we have a get statement on k2. So we know this put statement happened before this get statement. Then the next statement, b. So b puts a value for k1, which is v1. And we also know now this event happened before this event because it's on the same client. And now we can use the transitivity rule. So this event happened before this event, which is shown here. So we basically can say that we first have the put statement for v2, then the put statement for v1. So v1 depends on v2. Okay, let's continue now. So then client C gets first v1 and second a get statement on k2. Now the v2 is the important value. So let's assume the client sees v1, so the v1 is visible to the client. Then v2 must be visible to the client. Let's just assume instead of v2, here the value is v2 init, which was the initial value of the key. In this case, v2 would not be visible to the client, but v1 would be visible. So in this case, the causal consistency would be violated. As you might have seen in the gentle rain video before, we do have two constraints. The first constraint is we are using the physical clock timestamp shown here to ensure the causal consistency, which means if an object X depends on the version Y of object Y, then the physical timestamp must be less. And the second constraint is that we are calculating periodically the GST, which is the global stable time. And let's assume the GST value is equals t, then everything, or all versions that do have a timestamp less or equal to t are visible. So the GST only defines if something is visible or not. We also have an exception, which is the local visibility, but in general, this makes updates visible. Also note here, since timestamp depend on the physical clock, a clock skew must be considered, which is one improvement of CausalSpartan. And the second one is we are not allowed to modify the physical time directly because it also would have an impact on other applications running on the same server. Now let's come to an example when gentle rain actually lets the client wait for a request. So I've shown you before the constraint, which is the first one, which was the constraint that the physical time is less if you do have the dependency relation here. You see here the client pseudocode. And now you're going to see here one example. We do have a data cluster which has a physical time, which is shown here. So this is the physical times. And this here is the UT is the update time. So UT is the update time as shown here, and GST is the global stable time. The order is the following. The client is asking for a request. So this is our client. And the client for gentle rain usually stores DS, which is initially, let's say, 0.0. So first the request comes in. So pseudocode starts here. We are sending the request for key K1 here. Let's now ignore the GST because for this example it's unnecessary. Then the server is going to reply with the get reply. And it's going to send UT. UT is the update time of the current key. So in this case, it's going to send UT1, which is equal to 0.4. Then another step, the DT is updated with the maximum. So it's going to update to 0.4. So this is basically the highest timestamp the client has seen so far. Let's ignore GST. Now we're coming to the put statement. So the third one is going to be the put statement with key K2 and V2. And now let's observe something else. So we are having the get statement of K1, and then we are having the put statement K2 V2. But we know that the get statement happened before the put statement because everything is from the same client. So it's important then that the UT, the update time of the put statement of K2 is going to be higher than the update time of K1 here. So in this case, we're going to send here our 0.4 for our dependency time. And now this server here, this partition has an issue because the current physical time is 0.1 and the maximum time observed so far is 0.4. So what this server has to do, it has to wait until the physical time catches up to at least 0.4 to actually execute this put request. So this is the waiting time. And here, as I said before, we cannot change the physical time, so we actually have to wait until the physical time catches up, which increases the waiting time for put statements in case, as you see here, there is a clock skew, because here the physical time of two servers is different. Just a really quick recap. So what happens is we have three data clusters with three partitions. So the VVs are updated. We are focusing now on data cluster 1. So the VVs are updated from all other servers periodically through heartbeat messages. So then we're going to have the VVs. Then we're going to have the local stable time, which is just the minimum out of the VVs. Or here, whatever value. And finally, the GST going to be calculated, which is the minimum out of those values. So here it's going to be 0.1. So the GST is going to be calculated for every partition, and it's going to be 0.1 whenever all the informations are distributed. But because the GST is so important that only this value decides if something is visible or not. So in this case, we do have the server here, which stores the value of A. And it has three different versions, and this value here is the dependency timestamp. So what's going to happen, the GST calculation I've seen before is 0.1. So in this request, it's going to be sent to 0.1. And just because we had one server that was really slow, here only the last version is going to be visible, and this version is going to be finally returned to the client. So again, the reason was just because one data cluster was slow, this is an issue. Actually, it's because this value here, which came from data cluster 3. So the GST stays low if one data cluster is slow. So this gentle rain depends on having not a large clock skew also among data clusters, because the GST is just a scalar. I'm going to keep the next two slides really quick because we had this already in the class. So we have the HLC concept. We are combining the physical time and the logical clock, and we had this special scenario, or this scenario, maybe we shouldn't call it special, where actually the physical time and the logical time, the HLC time, are deviating over time. For the chain effect, you can see here. So we had to consider this in our algorithm, as seen on the next slide. Here, the final algorithm of HLC is shown, as already covered in the lecture. So again, the goal is we combine the best of the logical and the physical clock, and the idea is to keep the deviation, or to have an upper bound of the deviation between the logical clock, or the HLC, and the physical clock. Now we are coming to the first improvement of CausalSpartan. So we had the GST before in gentle rain, but now we're going to have a vector, which is the data center stable time DSV. Here's the pseudocode for the server. So let us go through an example. So now instead of just having the DST, so this was the DST before in gentle rain, now we're going to have the whole vector. The vector is going to have for each data center one value, and we're going to send this for our request. Then also each value which is saved in a server now has not only one value but stored three values here. So in this case, we are now comparing all values with each other, which is shown here in the pseudocode, which is basically the idea of the vector clock we have seen before, because we are now comparing each value. In this case, you can see 0.4, 0.4, 0.1, 4.4.4.1 seen over here, and it's the less or equal relation. So in this case now, the latest version is going to be returned to the client. So we don't have the issue of a single data cluster or single server in a cluster being far behind and versions become much later visible. Also, instead of the GST, we need now to update the DSV also globally or locally at each server in a cluster. Now, another improvement is we are using now HLC instead of the physical time. If you remember before, we had here the waiting loop because the data time here was 0.4, so we had to wait until the server here with the physical time, if the PT catches up. What we can do now is, because we are not changing the physical time, so we can actually say we have an HLC time, and we are simply changing the HLC time when updated. So we don't have to wait, we just use an update, and so the put wait request is not necessary anymore. So the key is we can use HLC. It has no effect on the application because it's now a mixture between a logical and a physical timestamp, and we can, doing that, increase the throughput by doing when we do put operations. Now let's talk about the results presented in the paper. So here we have x-axis shows the clock skew. So if the clock skew is increased, then obviously the trend is also very increasing for gentle rain. This is because the waiting time for the put statement of course increases if the time is different between servers. On the other hand, you can see here we have the gentle rain at the CausalSpartan, which has almost no effect, which is almost invariant to clock skewness. On the other hand, we do have also an overview of number of data centers. As you can see, the trend here is constant, almost same as here. So having more data center does actually not change the put response time effectively. Now we come to the results for the update visibility. So basically what we want to see here, that if the location of data center affects the actual update visibility. So this location here is much closer, obviously California, than Singapore. So this is increasing. As we can see here for CausalSpartan, it's almost unaffected, keeps constant. On the other hand, for gentle rain, the update visibility is increasing. So this again is because the GST is substituted now by the DSP, which is a vector. We actually keep track of the data centers independently, so this effect levels out. Almost the same on the other side, it's the update throughput, but here in case of increasing, we can see that the CausalSpartan, the throughput, keeps on being high, but for gentle rain it keeps on decreasing. So it's actually almost the same chart, but just the other way around. Now finally the paper presents an impossibility result. So the assumption we made is one client speaks only to one data cluster. Now let's assume one client speaks to more than one data cluster. Then it's impossible to guarantee availability and causal ++ consistency. The ++ indicates first that conflicts are resolved. So in case if two values are written for the same key are written concurrently, we need to resolve the conflict. And the second plus indicates that local updates are immediately visible. Now the whole proof is a proof by contradiction. We have two replicas R and R prime, and the connection between the replicas is interrupted, so no replicate message goes through. Then we have a client C. A client C first receives the first value for key 1, and then second puts another value. So in that case, we would append another value, P111 here. Then the second put statement, we would append another value here. And also see these are two put statements from the same client, so we know this put statement happened before this put statement, so we can actually say that the second value or version depends on the first version. The same as we had in the practice slide for causal consistency. Now the second client is getting or receiving this value here, which is the first one, and then this client is speaking to the other replica and is asking for the value of K1. So the client didn't receive any update so far, so it's going to return V01, which is shown here. And why is this violating causal consistency? Because we know, I'm going to show this again, it's the same what I wrote above, depending on V1, 1. So if the client sees V12, then also V11 must be visible. But here it doesn't show V11. In this case it shows V10, which violates the causal consistency. And this is the proof for contradiction. Again, everything a bit more in detail is shown here, but this is the main idea of the proof.